get to do this one talk on the microbiome and one talk on the metabolome, but we decided that these topics were inseparable, and so we're going to be switching on about during the talks. So there's very rapid advances in these fields, and they're really changing what we think it means to be human. But I'd like you to take just a moment to consider what you saw when you looked in the mirror this morning. We started out as it was just 43% human. Then I got here and I found it was my copy, and I think it dropped down to about 33%. But where that 43% number comes from, when we think about what makes us up as human, we have about 30 trillion human cells and about 39 trillion microbial cells, according to the latest estimates, but they are about and so on. So that's where that 43% number comes from. But then, as you did this morning, when we think about the level of DNA, we have about 20,000 human genes to 20 million microbial genes. So about 8 million figure comes from HMP1. In the phase 2 with that, we've had a whole lot of additional genes, and so on, and get us later too. And so by that measure, we're basically 1% human. And there's a lot of excitement about systems biology and systems medicine, but it's really hard to do that when we're neglecting 99% of the system, as we do when we disregard the microbial side of ourselves. Now, you've probably heard about the HMP and the tremendous achievement of the HMP and producing the record data set. And I went and counted the statistics that basically this project collected a total of 4.5 trillion A's, T's, C's, and C's. Right? And so the great thing about this is we have a lot of data, but that was also the terrible thing about it. So when I show you the first file of data from the HMP, despite the fact that what we're fundamentally doing is ecology, it's pretty hard to tell who lives where in the environment from this, right? And this is just the first file of this data. There's another 17,000 just like it, and this is the first 0.1% in the contents of that file. And so we really have to point that for us. This is especially problematic now that this kind of thing is in the hands of ordinary members of the public, right? Because through crowdsourced projects like American Gut and through various companies, you can now get your microbiome profile done, and so you have people coming into their doctors and saying, hey doc, I have some great news for you, which is I have my microbiome done. Now I have a list of 1,000 microbes that work in my gut, or even better, I have a double shotgun, and I have this list of 1 million genes that work in my gut. With all this data, you can tell me what's wrong with me, right? And I mean, what are you going to do? You can refer them to your colleagues in psychiatry who are being crazy enough to bring that stuff to you, and if they can interpret it, look at the evidence you have, right? But what our goal is as a community is to make it not crazy anymore and figure out how can you get something out of that profile, even with other data from the same period of time, or with the records data set. So you heard briefly about China this morning. When we applied China, molecules developed to the HMP data, you take all those sequences, you get this much more interpretable map. So what's going on in those maps? Each point represents more the complexity of the microbiome as read out by its DNA. Typically with 16 bits, but you can use these techniques that show genetics, so the transcriptomics are able to see to some extent camera as well. And when we color that data according to the mixed variation of my samples, you can see immediately that we can go down each of these samples, different parts of the body, are very different from one another. When I highlight the face, you see they're using the mouth and the gut, are totally different regions of the snap, almost have different continents. And it was really only when we did the microbiome project, looking at tens of thousands of samples from across the Earth's surface, that we understood how profound these differences on the human body were. Because what we can do is we can go out on the middle surface, we can have about 2 points on the planet surface, and just as distant from each other as the mouth and the gut of this one person. And if you think about your mouth as being maybe like a coral reef with complex mineralized structures covered with biofilms, good infrastructure of that, the amazing fact is your mouth is far from your gut and its microbiome is water and that reefers from the dirt and it's very, so they're essentially non-overlapping communities. And that leads us to wonder where do these highly differentiated communities we have as adults come from in the first place. And if you have dogs, I'll get to you, we have dogs suspicions about that, and all of which are true by the way, so I can actually match you up to your dog with fairly high precision based on your microbiome, and even your dog's microbes that they tell you to develop. But in all seriousness, as Gloria will tell you on Friday, how we're born has a tremendous impact on our first microbes and then how we subsequently develop. So I'm not going to show you that, but I will show you the value of longitudinal data. So this is what we did with Replay, looking at the development of the gut microbiome of one child over the first 2.5 years of life. And you can see that the first fecal sample looks nothing like a healthy dog gut sample. So it's up there in the back region of the plot, which we would actually expect from the child's delivery weight. What I'm going to do is just take a couple of points one to the next, so you can see the 2.5 years of development at 1 week intervals. In case you're wondering why 2.5 years, that's when we get the toilet trained. It's a lot easier to get a fecal sample out of the diaper, but to find someone who's scrambling with a brush. So anyway, so I'm going to start this going. And what you can see, sometimes there's tremendous variation 1 week to the next, other times it's just a little variation. And sometimes the distance traveled in 1 week is greater than the difference between any 2 healthy adult samples in the HMP. So if you think your child looks like a different person 1 week to the next, that can literally be true in terms of their microbiome, where most of the genes are in the first place. But coming up here is a full backstage. So what you're going to see is the antibiotics for an ear infection. You see a tremendous regression of the microbiome, followed by rapid recovery. That went by pretty fast, so I'm just going to rewind it for you and play it for you again. What you're going to see is auto administration of oral amoxicillin. We see this tremendous reversion of the microbiome during months of normal development, followed by relatively rapid rebound again in just a few weeks. And then by the time he's at 2.5 years, you can see that he's basically in a healthy region of the plot. So what we're trying to figure out at the moment, and then again, everything I'm showing here is just taxonomy. So just in the case, what we're trying to figure out is why are some people resilient and other people very fragile to this kind of microbiome change. So we started to address this in trying to determine the chemistry associated with your microbiome. We started to address this by answering a very fundamental question. What kind of molecules does your microbiome produce that can control proliferation and colonization of a variety of pathogens? And so the first thing that we did is we made everybody work out in the lab, and then we had them isolate, basically use hand swabs to isolate different microbes from them. If you were to do this exercise on yourself, what you get is you get organisms that look like this. This was absolutely beautiful. But basically, anybody who will be able to see these kind of microbes that even like football has, it looks like really unusual features, color red, and so on. But we then take these microbes and we culture them pathogens, so we develop something called microbial imaging mass spectrometry that allows us to actually look at the chemistry associated with these microbes directly from feature images. And so what you will see here is that this bacillus that came from a ton of other individuals that we sampled from, that it produces a red molecule, there's a gradient of a molecule, but then you start to see these blue molecules, these are delta toxins, phenolphthalein molecules in staph synthesis that are produced by staph aureus. And these are purely factors that allow staph aureus in very healthy individuals. And so based on this image, what we proposed was that if this red molecule is present on the skin, maybe it suppresses the production of these virulence factors, maybe you get a decreased ability for staph aureus to colonize these skin environments. And that's a testable hypothesis. So we isolated these particular molecules, we then add staph aureus to it, and we simply ask the question, how many colony-forming units of staph aureus can you isolate from this? And what you will see is that upon treatment with this particular molecule, you see about a 75% reduction of colony-forming units that you can observe for staph aureus. And so that supports the hypothesis that you can organisms to live on us, that they produce molecules that can control at least the colonization and proliferation of pathogens. But we actually pushed this a little bit further, and we wanted to see if these kind of organisms that produce these kind of molecules, what impact that have on health and disease. And that ended up being published in this paper with Rich Geller and Carsten Sengler, who's here as well. But essentially, we took healthy microbes, we added the creams, and to atopic dermatitis patients. And what you'll see is you see a decreased amount in atopic dermatitis symptoms, and it's related to the suppression
of staph aureus. So there's really an important relationship there. But this is an artificial system. Here we're really literally overwhelming the system with these healthy microbes. And so the question that I have is this really a normal condition that might be present on the skin? And so the reason why I ask that is because these molecules have never been directly detected from the skin. And so we wanted to come up with technologies that would allow us to see the chemistry associated with it. And that actually led to our first research paper, joint research paper with Bob Knight, where we started to map the chemistry in the microbial communities in 3 dimensions on the human surface. And so the idea is actually simple. If you spatially collect both the molecular information as well as the microbial or it could be that the microbes produce these molecules, or that they modify molecules that are present on these different regions of the skin. And so, just to show you a very first data set for metabolomic data, that's this movie right here. But what you will see in the upper right-hand corner are all the molecules that we're able to detect by mass spectrometry. And then in blue, it's low concentration, and red is high concentrations of these molecules. And so what you can see, as we're scanning the molecules, the MOSEs, you can start to see it sort of flickering. What this is essentially telling us is that there are different chemical distributions that exist on the skin surface. And when we stop these movies in time, what you will get is you get molecules that are associated with the belly button, molecules with the hands, molecules in the groin region, shoulder region, molecules that are uniformly distributed throughout the entire surface, but also some molecules that are low in concentration on the head, and as you go down your toes, it increases in concentration. And so if you're a microbe and you want to find your ecological niche, where in that gradient does it fit? And we have very little understanding of this. But what that allows us to do now, we also got 16S inventories of this, and we can also create these corresponding microbial maps. And so here we're looking at propionic there on the chest, back, and head area, and there's about 850 genera that we were able to detect in these particular studies. And so now what we can do is you can take advantage of the spatial information and say, okay, what microbes are co-correlated with the different molecules that are present, and can we use that to understand why those molecules are there or what the molecules are doing. And indeed, we were able to find a series of molecules that were associated with the degradation of triacylglycerides, and that you can recapitulate in vitro. When you take a propionic bacterium and add triacylglycerides to it, you can start to see the degradation products such as lactic acid or even the oxidized version. So what this basically meant is that microbes not only just contribute molecules that are present on the surface of the skin, but they also can modify existing molecules that are present there as well. But the data set like this really, it generates has the capacity of generating many different hypotheses. And this was recognized by Francis Collins when he blogged about this particular paper, that this kind of data, essentially, as he said, this kind of data can generate lots of hypotheses. But how do we continue to learn about knowledge about a data set like this? Well, for the metabolomic side, we built this crowdsourced analysis infrastructure. This is a worldwide effort, basically, with 127 authors that we published. But what this is a place where you can deposit all your data. So it's the largest metabolomic repository at the moment. It has about 3 billion spectra in it. But you can make annotations to your data, or anybody else in the world can make annotations to your data. And if those annotations match to other people's data, they will get that information related to them. And so you really built this community knowledge associated with metabolomic data, and it's also a way to capture that knowledge. And so the knowledge is clearly growing very fast, and what you'll see is there's individual contributions, and sometimes you have large contributions, such as the one from PNNL here. Sorry, I accidentally hit the wrong button. But the skin data sets, it was clear that the knowledge about this particular skin data set was growing very fast as well, because initially when we deposited the data, we had 98 annotations, and by now we're 772 annotations, so it's really grown very quickly. But at one point we got an email where they were saying, oh, hey, you have these degradation products right here that come from heme degradation, and because somebody in the world was studying an organism that was actually degrading heme, and they made these annotations, and we found those in our human maps. Where did we find those? Well, they were in the groin region of the female. Now, we'd already seen in the paper when we published it that heme was present, and that was consistent with the fact that she was on the late stages of her menstrual cycle. But what it shows was that there's now a possibility that there is some process there that is involved in the heme degradation. And one of the things that we can look for are microbes that sit in that particular region. And you can actually look if any of these organisms have this heme oxygenase. And I know Streptococcus has one of those heme oxygenases that is present. And so now you can build a hypothesis that these microbial communities are actually involved in the normal physiological process that affects 50% of the population. But if you really want to determine which one of these organisms is truly responsible for that, longitudinal studies would probably be ideal to do that.
Absolutely. And so we've been getting more and more into longitudinal studies of the kind you saw this morning with HMP2, which we think are critical for understanding therapeutic response. And this is sample snapshot data around that. So, for example, in American Gut, we've had over 10,000 people sign up to send in their samples and get them analyzed. Of course, not everyone wants to know what's in there. These are middle schoolers staring at lab, learning to use lasers and robots to study bacteria and food. But you can get so much more out of the time series in this single snapshot, and especially when you integrate with data frames like the HMP data. So this the live time series shows you what you can get integrating with the HMP. In this case, we get to look at C. diff infection, and this was a collaboration we did with Mike Stansky and Alex Griggs at the University of Minnesota. But when we look at the fecal samples from C. diff patients, you see those spiky symbols there. They're totally different from the healthy stool down the bottom. And what's going to happen is that 4 of these patients are going to get kills about 40,000 people a year. So anyway, the questions are very much like the questions that I showed you with the time series. And we now, instead of taking a week, each frame is going to be just 1 day. Patients get in the sequence of blood, and you might wonder, given the C. diff is the underlying pathogen, will you even see any effect at the whole community level when you do this? And what you can see is that essentially immediately, so just 2 or 3 days, multiple patients move their microbiomes completely into the healthy state, and then they stay there during the months of follow-up. And this has happened to remission of all the clinical symptoms. In fact, the last trial that was done to directly compare fecal transplant to antibiotics had to be stopped early because the fecal transplant was over 90% effective. The antibiotics that are standard of care were less than 40% effective. So it was considered unethical to continue with fecal transplant unless the antibiotic out of the trial. So they all got remission and recovered. But what's amazing about this is that it shows you how the microbiome over time can show you your progression through this therapy. Now, shortly after we got to UCSD, Larry Smart, who's at Director of LIT2, was looking at the HMP data with me on the 64-minute pixel display ball, and he said, well, Rob, I have a very interesting microbiome myself because I'm an IBD patient, and how can I get myself back out of that? And that led me to institutions know that when you do this research, you get the same amount of African colleagues, and in my case, it's literally true. But Larry's been fascinating with studying himself for the last 17 years, looking at what dimensions of weight, and adding dozens of dimensions to still tests, dimensions of separate value, and now dimensions of 16S, and also showing metagenetics. And I've been studying the microbiome for a few years, and he got this very text on each other, and you don't see patterns in there. Now, is just this is just one guy. Can you generalize this? And this is the way we did with Jeff's and a number of other collaborations, looking at the dynamics of many crazy patients with different forms of Crohn's. And when I studied animations going, what you can see is that the yellow and red traces, which are allele traits without surgery, there's a tremendous amount of variation. But then, for example, the healthy controls in green, or the ulcerative colitis patients in blue, who are very late overall. You can also see that there's this area of visitation to the healthy region, even in people with IBD. It's difficult to tell what's going on from a single time point. So we figured out how to mathematically model this as a healthy plane. That we're looking at distances from. So the top row is a cartoon of how we measure the healthy plane, and they measure the distance of each point from it. The bottom is the actual data with two different distance metrics. And what was amazing about this is that we actually got measures of these classifications from this microbiome-based assay that we call protective, which is currently the gold standard. So looking at time changes is one of the ways that we can begin to understand the changes that happen within the microbiome. But spatially, you can also do this, and really, it's an opportunity to integrate multi-omics information. And so I'm going to highlight this with this particular highly interdisciplinary study, and that is led by my former postdoc, now a faculty member at Georgia Tech, Mayor Gard. And she was fundamentally interested in what are the chemical environments associated with these microbiome communities that actually exist within a cystic fibrosis lung. And so one of the things that happens in cystic fibrosis is that your lung function diminishes. And so when your lung function diminishes so significantly, you get put on the transplant list. And so what Mayor Gard was able to arrange was that we would get these old explanted lungs from these patients, and then she would section these in several hundred pieces and subject these to both metabolomics analysis as well as 60 hours inventories. And so then what you would do is you essentially map this data onto the CT scan of these individuals to gain spatial insight in terms of the distributions of the microbes as well as the molecules that were present. And using the co-localization strategies and really creating networks of co-localization of molecules and microbes, she was able to formulate a very interesting, or she was able to observe something very interesting in that there are actually microbial interactions that take place that change the metabolism of these organisms when they're interacting. For example, here we see these quinolones, and quinolones are known to increase biofilm formation in Pseudomonas aeruginosa, and maybe that's why we get a local decrease in lung function when you get an increase in the amount of these biofilms that are created. So, but this is one observation that she had. There's a lot of other things that we're able to observe. So we, for example, can see the distribution of antibiotics. In this case, I'm just showing you 4 of them, but we found at least 20 of them. But notice some of these really interesting gradients here. It looks like either the drug is only partially penetrating, and this was a really interesting observation because that suggests that maybe there are microbial gradients that exist within these lungs as well. And so she was indeed able to find some of these microbial gradients where you look at these gradients of antibiotics on the left here. And one of the things that we notice is that we started to see other microbes that are typically not, you wouldn't think of a lung to have anaerobes present, but where we don't see these microbes or antibiotics penetrate, we start to see an increase in anaerobes. And so the question that we had is, well, what's really happening to these antibiotics here in these type of gradients, and how can we test this in this more in vitro model? And so Robbie Quinn in my laboratory, Project Scientist, he came up with a system where you have basically a capillary tube, actually not a capillary, it's a 10 millimeter tube. The bottom of it is sealed, and you add sputum to this. And so what you now have is you have a zone where that is oxygen exposed, and then the bottom part essentially becomes anoxic. And so we were able to use this to recapitulate the phenotype that we were able to see within these lungs, where you have oxygen-loving organisms, even though Pseudomonas can grow all the way into the anoxic zone, but we clearly see some anaerobes that are present in these particular samples as well. What is nice when you have such an in vitro model that you can recapitulate some of this information is that you can alter the conditions. So, for example, you can add antibiotics to it. And one of the striking features that we saw is when we added antibiotics to it, such as tobramycin, which is an inhaled antibiotic that's commonly used in cystic fibrosis, we actually could barely detect the tobramycin itself in 16 out of the 19 patients that we tested, whereas in 3 of the patients, there was no degradation or disappearance of the tobramycin antibiotic at all. And if we look at the sequencing of those particular patients, those 3 patients, we observed something very interesting. Using FIFO amplification, we actually saw that there was an abundance of aspergillus mitochondria there. And of course, the annotations using FIFO amplification mitochondria is not that strong in terms of being able to annotate and confirm that this is aspergillus, but this is where multi-omics really come into play. And in fact, we also see a lot of aspergillus fumigatus-derived molecules in those same zones. And what this suggested was that upon antibiotic treatment, we were removing microbes in these patients, allowing aspergillus fumigatus to thrive. And this is a common problem in cystic fibrosis where you get these aspergillus fumigatus flares. But one of the questions that I had was, well, what's happening to the tobramycin? Why is it disappearing in those other patients? Well, we used molecular networking, which is a unique analysis tool that we've introduced in 2012, but is now part of this community resource. It allows you to make relationships between the molecules that are very similar. And one of the things is you can very quickly see that there are a lot of degradation products associated with this tobramycin. But in this one patient, it was very interesting. It was the only patient that had the majority of this. And what we ended up finding out is that it's actually modifying this nitrogen here with a propyl group, but only in the anoxic zone and not anywhere else. And so this is a new modification that has not been demonstrated before, but it shows that if we start to look at these kind of lung environments into these gradients, we may actually find new mechanisms of antibiotic resistance. So we're also speculating about the future about where this could all ultimately lead. What we'd like to do is we'd like to get this stuff out of the realm of the lab, where you need millions of dollars in mass spectrometry and sequencing equipment, and into the clinic and perhaps even into your home. And the concept of the microbiome and metabolite analysis should be as easy as exactly as it's already been tested, things like cystic fibrosis conservation and placebo, so that's perhaps not that implausible. And the idea is you can get instant molecular readout, presumably with a better user interface with this, but on your mirror as you look at it. We can use the same kind of technology that some people translate to turn that into a microbiome profile like we get out of an American gut, or alternatively perhaps it needs to connect to your smart toilet to read out the last data from there. And then the idea is that we can integrate it with large multi-omics resources, such as CHMP, to identify when you're at risk for a particular disease based on changes in your individual microbiome profile. And then if there's anything that you can try at home, or if there's something that you need to talk to a physician about, and then you can even imagine having that communicate back to your smartphone. So when you're faced with 1,000 times in yoga on the supermarket, you can use augmented reality to zoom in on the one that you're trying to find and then scan the barcode to confirm that you've actually got it. And while this might sound like as in science fiction, if you talk about, say, a crazy supercomputer from 30 years ago, the idea that you would hold in your hand the thing that took the size of a room and required a team of technicians to keep it going, and that there would be networks to 1 million others worldwide, and that you wouldn't need any training to get started with it. That's amazing, right? So the idea that we get from better user interfaces, not just for instrumentation, but also for microbiome stuff as well. So that's the kind of thing we're trying to put together and using San Diego. Just to finish this again, when you could do this, what kind of insight can you get right now from current technology into the disease process through these multi-omics techniques that otherwise you might miss entirely? So that gets us into a case study. So Bob and I have implemented a program where we can give fairly efficient feedback in terms of functional understanding of what's happening to the microbiome. So this was an adult female who was 39 years old, long history of heart problems, or 4-year-old history of heart problems. In fact, in 2012, her heart stopped beating and she had to be rescued, and fortunately they were able to. The cause was never established. And so then in 2016, she again started to have many major heart problems. In fact, she would have a heartbeat 55 hours.
What you can present is a very simple model where the set of genes and their abundances in the metagenome is really nothing more than the aggregate genomic content of all the species in your community weighted by the relative abundance. It can be represented as a simple mathematical mathematical set of equations. Now, what we have here is a very simplistic model between taxonomic composition, genomic information, and metagenomic information. And this model is not new or surprising. We don't think about it when you're doing metagenomics. Like 5 years ago, an hour long, we're using this perfect metagenome based on the species composition. What is surprising is how rarely we actually use this model when we try to analyze gene composition and species composition in parallel. And I'll show you a few things you can do. Maybe the simplest thing you can do is to visualize those flips. So this is a screenshot from a browser that we hope to release in a couple of months. It's called Burrito, and it will basically given taxonomic information and metagenomic functional information will show you those traditional bar chart of all the species that you have and all the function. You can look at the different resolutions, but it will also highlight all the links so that if you now click over a specific taxon, it will show you using those radios here what part of the metagenome is being contributed by this set of species that you select. Right in large versions. So use it as a way to explore taxonomic variation and functional variation while accounting for the way these two are linked. You can of course use things that are much more sophisticated. For example, several years ago, a postdoc in my lab showed that in cases where you do not have genomic data, in other words, you sample include many species for which you do not have genome, but you do have taxonomic information and functional information, you can use this model as a way to deepen the genome, basically figure out which gene in your metagenome must be associated, must originate from the species in the metagenome simply based on resolving these set of linear equations. A couple of years ago, the graphic in the lab shared a group who was specifically focusing on the cases where this model fits, or what we expect to find in the metagenome based on what the taxonomy tells us and what the genome tells us, and actually not what we find in the metagenome. And the reason for that is because of string variations, what we heard about, say, about time today, and was able to use this to characterize extensive string variations in the metagenome across numerous samples. Other groups in the lab show again that this model can be used to correct functional data, specifically to address a problem that we'll face with how do we normalize functional data. And so Rob tries to use this idea of composition normalization. When we look at the relative abundance of each function, we know these days are common problem, but if we take this model into account and actually use genomic data to re-normalize your metagenome, we've shown that by doing that you can figure out associated shifts that are much more correct. And finally, something that we published just earlier this year, again, if you account for this model, trying to figure out why do we see this tremendous variation on the taxon level, but the relatively little variation on the functional level, you can show that at least some of these uniformity that have become one of the puzzling canonical results in research has to do with the way that we normalize functional data. If you take into account this link between taxon, genome, and metagenome, you can in fact reveal quite dramatic hidden variation in the functional data.
はい、ありがとうございます。1.226円頂戴いたします。セーブの私。どうもありがとうございます。またお越しくださいませ。どうぞ。お待たせしました。お預かりします。1.280円ですね。それではお入れいたしますか。失礼します。品物ですね。こちら失礼いたします。110円からのお預かりですね。2円のお買い1人ずつでございます。ご確認ください。1円オペします。216円ちょうだいいただきます。レシートでございます。どうもありがとうございました。There's a very specific set of taxonomical targets that you can address in order to reverse this specific functional shift without actually changing other functional profile of the microbiome. This idea of specificity between the contributor and the functional shift is something that we saw in every database that we analyze. We turn out that those contributors are side function and disease specific. This is just another example that I thought was interesting. So if you look at the metagenome of patients both with type 2 diabetes and inflammatory bowel disease and compare them to control, you find that in both of these four you have an enrichment of genes that are involved in metabolism. But if you run FISH.org, what you'll see is that the underlying taxonomic contributors are completely different. So again, if you're trying to use this for social indication to figure out what is your intervention target, it will have to be very disease specific, even though you're dealing with the same kind of functional imbalance. Again, FISH.org is available online. There are several labs that will be working with that, published with that, and we have actually a web interface that will generate those forms that I've shown you before. The last thing I would say that this approach of using a model to link between different omics is not limited just to species information and gene information. This is a project by another graduate student in the lab. The tribe going to use the same approach to link the species information of the part of the microbiome or another way to the metabolite. And again, rather than trying to find association and explain them in retrospect, she was trying to build a model using genomic information, metabolomic information, some metabolic modeling, and genetic database, and trying to build a very simplistic computational model that's linked how the composition of species in the microbiome look like to the concentration of different metabolite. And the basic question that's going to ask is this model sufficient to explain the concentration or the variation in concentration of metabolite across different samples? And again, I'm not going to go into detail. The basic answer is that yes, we can do that at least for a substantial fraction of the metabolite. Just looking into which species are there and what are their metabolic potential would allow us to explain the variation that we see between the concentration of metabolite across samples. Again, this is a tool that is available online from Munza. We're now working on a second version of that that will hopefully be much more accurate, but you're welcome to calculate that of interest. And so I think aligned with that, I'll just conclude with this slide about critical gaps and challenges. I want to echo everything that was said in the morning about the knowledge gap, which as somebody that is trying to build models and hoping that this model be as complete and as accurate as possible. The main challenge we have in those missing functional notation is something that in the lab we formally call the microbial gray matter. So it's not the dark matter. There are sequences that we don't have, and sequences that we have we just don't know at all what their function might be. But I do want to emphasize again what I think is a bigger challenge is how do we move from knowing what's in the microbiome to understanding what the microbiome is doing. And I think in order to do that, we have to develop some kind of framework that will take the genomics and apply them into a model that's approach that is very balanced with association. And I want to emphasize that everything that I showed you today is really just a simple diagram in terms of what's there are many challenges involved. Whenever you build a model, we're going to try to build a model that which is scale and resolution and dynamic and time frame. And all those things are not resolved, and all the challenges that we're going to help us do. And so with that, I will end
see SNPs, polymorphisms that would be in the mom, down to something that's 10x coverage if there's one read out of 10, so 1/10 of her cells, basically, amongst the sampled cells, having that low, less prevalent strain. So something below that wouldn't be detected if there was only 10x coverage. For some of the species I talked about, we actually have hundreds of x coverage, so then the resolution goes lower. So we can report a sort of a sensitivity for every species that we analyze, and it's great for some of them, and it's really not as great for others unless you do a lot more sequencing.
And so therefore, I might modify the conclusion. But the other possibility is to try to sample the moms more deeply, and so that you can have a better denominator basis for this based on the limitations that you mentioned.
Absolutely. This was data mining a publicly available data set, so we were, of course, our hands were tied in terms of more sequencing, but that would be an important thing to do to test the hypothesis that we generated.
It's really hard to you.